Hi there, Serdar Yegulalp here for InfoWorld at IDG. Today I'm going to show how Python programs can be made to use multiple CPUs by way of the multiprocessing module. By default, Python programs run in a single physical thread. That's because the default Python runtime is single-threaded for the sake of simplicity. If you have a Python task that's CPU dependent and you want to use hardware threads to speed it up, you can use the multiprocessing module to do this. Multiprocessing works by creating a pool of Python interpreters, typically one interpreter per CPU in your system, but it's tunable, and then allowing you to feed jobs to that pool, which are then executed in parallel. Because launching the process pool itself takes time, you typically want to do that once at the start of a program, and then just feed it jobs as needed. What I'm going to do here is take a simple benchmark application and show you how multiprocessing can be used to speed it up. The benchmark reads a large CSV file taken from Google's Ngram database, about 187 megabytes, and tallies some statistics from it. On my system, an i7-3770K processor, it takes around 11 to 12 seconds to run the benchmark. Multiprocessing usually works one of two ways. The first way, you take many little jobs that are CPU dependent and submit them to the process pool. The second, you take one big job and find a way to slice it up efficiently into many little jobs. The benchmark we have here fits in the second category. It's a big job that can be sliced up. We're reading a file line by line and gathering statistics about each line, which we then aggregate at the end. Multiprocessing gives us tools to work with both kinds of jobs. And so in this case, we're going to be using the IMAP unordered function, which takes an iterable, like a file, which is read line by line, and parcels it out piece by piece in round-robin fashion to processes in the pool. Each process runs a defined function on it, in this case our simple statistics gathering function. Now let's run the multiprocessing version of our benchmark. As you can see, it runs much faster. It doesn't provide an absolutely linear speed up with the number of cores in the system, but that's fine. Any improvement is better than none, and it's actually harder to get an absolutely linear speed up with more cores in many cases anyway. One important thing about multiprocessing to keep in mind is inter-process overhead. I mentioned earlier how there's the overhead of launching the process pool, but if you keep that confined to program startup, it's less of an issue. But the other kind of overhead you need to remember is the overhead involved in communication between the main process and the process pool. Each time the main process sends a job to the pool, and each time a job returns a result, there's overhead involved. So to reduce the effects of that, we want to keep the total number of round trips between main process and pool as low as possible. Multiprocessing has a few built-in ways to deal with that. For instance, you'll notice this parameter here named chunk size. This is how many slices we send to each pool process at a time. For a large job like this, you want to set chunk size quite high. In this case, the main process is going to read around 16,000 lines or so at once, and sends that in one big chunk to the first process. Then it reads the next 16,000 lines, sends that to the next process, and so on. This is faster than going a line at a time, because you can bundle that many more lines in a single transaction. On the other hand, if you set chunk size too high, you'll end up losing performance since the cost of sending larger chunks starts to become its own burden. Doing things in a multiprocessed way brings other kinds of risks you need to be conscious of. For instance, you always need to be aware of how a multiprocessing job contends for resources. In this case, the main resource is the file we're reading through, and Python automatically handles contention for it since all of the read operations are in a single thread. But if you have multiple jobs in a pool, all fighting to read the same file on their own or contending for some external resource, you lose most of the benefits of dividing up a job across physical processors. If you like this video, please leave a comment below. Don't forget to subscribe to our IDG Tech Talk channel on YouTube, and for more Python tips, follow us on Facebook, YouTube, and Infoworld.com.